Alright, Neets Module 9, Chapter 2, Oscillators. Learning objectives. Upon completion of this chapter, you will be able to list two broad classifications of oscillator wave generators. Identify three frequencies, determine the levels of the sim wave oscillators, determine the difference between series fed and shunt fed oscillators. Explain how crystals is equivalent to the series and parallel induction capacitive circuits. Identify the Armstrong oscillator. Identify the Hartley oscillator. Identify the Colpitts oscillator. Identify the resonant capacitive oscillator. Determine the frequency of resonant capacitive oscillator. Explain operation as a pulse oscillator. Determine how many cycles are present in the output of the pulse oscillator. Explain how frequencies of multiplication takes place. Wave generators play prominent role in the field of electronics. Generated signal with a few of the hertz, a single gigahertz, or 10 times 10 to the ninth hertz. Modern wave generators, many different circuits generate such output that the synthesital, square, rectangular, sawtooth, and trapezoidal wave shape. The wave shapes serve many useful purposes for the electronic circuit that we'll be studying. For example, they are extensively throughout the television receiver reproduce pictures and sound. One type of wave generator is known as an oscillator. Oscillator can be regarded as an amplifier provided with its own output, which provides its own output in its own input signal. Oscillators are classified according to the wave shape that they produce and requirements needed for them to produce oscillation. Classification of oscillators and generated wave generators can be classified in two broad categories according to their output wave shape: the syncytial and non-syncytial. Syncytial oscillators. The syncytial oscillator produces the sim wave with the output signal with the output signal with a constant amplitude but with no variation in frequency. Actual something less than is usually obtained. The degree to which they ideally approach it depends upon the such factors as the class of the amplifier operation, amplifier frequencies. Amplifier operations, amplifier characters, frequency stability, and amplitude stability. Since sim wave generators produce the single range signals ranging from low audio frequencies to ultra high radio and micro frequencies. Many low frequency generators use resistors capacitors to form their own frequency determining networks referred to as resistor capacitor oscillators. They are widely used in audio frequency range. Another type of sim wave generator is the inductor capacitor frequency determining the network. This is known as the LC oscillator, or inductive capacitive oscillators, which use the tank circuits that are commonly used with the high radio frequencies that are not suitable for use with extremely low frequencies. Oscillators, because the inductors and capacitors would be larger in size, heavy, and costly to manufacture. The third type of the sim wave generator is a crystal controlled oscillator. Crystal controlled oscillator provides excellent frequency stability in the middle of the auto range and through radio frequency ranges. A non-incidental oscillator. Non-incidental oscillators generate complex waveforms in square, rectangular, trigger, say, sawtooth or trapezoidal. Because the outputs generally characterized with the sudden of the change, relaxation, often referred to as relaxation oscillators. Signal frequencies for the oscillators usually governed with the charge of the discharge time of the capacitor and served with the resistor. Some type of however, that contain inductor for the effect of the output of frequencies. Thus, like syncytial oscillators, both the resistor capacitor and the inductor capacitor networks are used to determine the frequency of oscillation. Within the category of the non-syncytial oscillators are multi-vibrators, locking oscillators, sawtooth generated trapezoidal generators. Basic oscillators. An oscillator can be thought of as an amplifier to provide itself with a thorough feedback with an input signal. By definition, non-rotating device producing the alternating current with the output frequency which is determined by the characteristics of the device. The primary purpose of the oscillator is to generate the given waveform with a constant peak amplitude with the same specific frequency to maintain this waveform in certain limits of the amplitude and frequency. The oscillator must provide amplification. An amplification in single power occurs for the input and output in the oscillator proportion of the output is feedback to the sustained input, as shown in figure 211. Enough power must feed back the input circuit of the oscillator to drive itself as does its signal generator. To cause the oscillator to be self-driven, the feedback signal must be input to the amplifier and output in a loop between the amplifier. The basic oscillator block diagram. Regenerative signals must have enough power to compensate for the circuit loss to maintain oscillation. Since the practical oscillator must oscillate with a predetermined frequency determined by the device, or FDD. Signal referred to as the frequency determining network, FDN, as neither the device acts as a filter, although allowing only desired frequency to pass. Without the frequency determining device, the stage will oscillate in a random manner where the constant frequency will not be maintained. Before discussing oscillators further, let's review the requirements for an oscillator. First, the amplification is required to provide the necessary gain with a single second is sufficient. Second is sufficient regenerative feedback required for the sustained oscillation. Third is the frequency determining device is needed to maintain the desired output frequency. The basic output oscillator requirements, in addition with addition to the application, determine the type of the oscillator to be used. Let's consider some of the factors accounting the complexity and unique characters of the oscillators. Virtually every piece of the equipment that uses the oscillator has two stability requirements: amplitude stability and frequency stability. Amplitude stability refers to the ability of the oscillator to maintain constant amplitude with the output waveform. The more constant amplitude with the output waveform, the better the amplitude stability. The frequency stability refers to the ability of the oscillator to maintain operating frequency. The less oscillator varies from its operating frequency, the better the less the oscillator varies from operating frequency, the better the frequency stability. The constant frequency amplitude can be achieved by taking extreme care with the prevent variations in load bias component characteristics. Load variation can be greatly affected with the amplitude frequency stability output of the oscillator. Therefore, maintain the load as constant as possible necessary to ensure stable output. As you should know from your study of the transistor biasing, bias variations affect the operating point of the transistor. The variations may alert with the amplification capable of the oscillator circuit as well as a well-regulated power supply. Bias stabilizing circuits are required to ensure the constant uniform single output. As a result of the changing temperature, humidity, condition, the value of the characteristic of the components, such as the capacitor, resistor, transistors can change. These changes in the components also change the amplitude and frequency. Output power is another consideration. Oscillator, generally speaking, high power is obtained with the sum of the sacrifice of stability. When both of the requirements are met, the low power stable oscillator can be followed by a high power buffer amplifier. The buffer provides the isolation between the oscillator and the load to prevent changes in the load affecting the oscillator. The oscillator stages must be develop high power, and efficiency becomes more important. Most oscillators use the Class B bias to increase the efficiency. Other type of the oscillators may use the Class A bias when the high efficiencies not required, but distortion must be kept in a minimum. Other classes of bias may also be used with certain oscillators. Sim wave oscillators. Resistor capacitor networks, indicative capacitive tanks and crystals may appear with a sim wave oscillator circuits. An amplifier can be made in the sim wave oscillator and provide regenerative feedback through the resistor capacitor network. Resistor capacitor network. Figure view 2 view A show the block diagram amplifier of the resistor capacitor network through which the regenerative feedback is provided. The resistor capacitor network also acts as a frequency determining device. The view B show the vector analysis of signal E at the various points for the circuit. Or show the input signal with the resistor capacitor 3 resistor 3 and capacitor 3 power the resistor 2 capacitor 2 resistor 1 capacitor 1 and M. The input signal base common and input signal base collector amplifier common emitter output signal. Figure 2b shows the resistor capacitor oscillator vector analysis. Resistor 1 N, resistor 2 P L and R and M. To analyze the operation of the circuit of the view A, they assume the amplifier with a common emitter configuration. The signal of the collector M is 180 degrees out of phase with the signal input with the phase on the base R. The circuit produced the regenerated feedback with the resistor capacitor network to provide 180 degrees phase shift with the collector signal. The power is applied with the circuit and the noise voltage. Noise containing the many different frequencies will appear on the collector. The noise signal represented with the vector LM in the view B. The signal couples with this capacitor 1 across the resistor 1. View A, the phase shift occurs. The voltage across the resistor 1 and the voltage of resistor 1 represented by the vector LN has been shifted in phase about 60 degrees, reducing the amplitude. The signal at point A, the signal at point N, view A, is coupled to the next resistor capacitor, signal resistor 2, resistor capacitor 2. Using the same size resistor capacitor as before will cause another 60 degrees in phase shift to take place. The single point P and voltage across the resistor 2 represented with the vector of LP. The single point of P has been shifted 120 degrees amplitude, reduced still further. Same actions occur at the last section, resistor 2 and capacitor 2. Resistor 3 and capacitor 3, the signal experienced another 60 degrees phase and had further amplitude reductions. Signal at resistor voltage resistor 3 has been shifted 180 degrees, represented with the vector of the inductive resistor. or vector LR. Note that the point R is in the input base of the common emitter amplifier. Also, the LR vector as the signal on the base regenerated, aiding circuit operation that meets the regenerative feedback requirement at an exact 60 degrees phase. A shift per signal per stage is required, but a sum of the three phases shift must be equal to 180 degrees. For the given resistor capacitor network, only one frequency of the initial noise time will be shifted exactly 100 degrees. In other words, the network frequency is selected with the effect of the RC network is frequency determining device, since the length of the vector has been relationship depending on the frequency of the differential frequency. Oscillation is governed by the value of the resisting capacitance of the section. Variable resistor capacitors may be used for providing tuning of the feedback and the feedback network to allow for the minor variation in phase signal of the resistor capacitor phase oscillator or the amplifier based on Class A operation minimum distortion of wave and signal. Or your LC network. Some of the same wave oscillators used for the resonant circuits were consisting of the inductive capacitance. For example, recall the tank circuit, which with the resonant circuit stores energy alternating with the inductor capacitor, provides the same waves used to study the action with the tank circuit in Chapter 1. If there is absolutely no internal resistance of the tank circuit, the oscillation would continue indefinitely, as shown in Figure 2.3. View A on resonant circuit, however, contains some of the resistance with the dissipates the power. The power loss causes the amplitude to decrease. As shown in views B and C, with the reduction in amplitude of the oscillator is referred to as damping. Damping is caused by both tank and load resistance. Larger for the tank resistance for the greater amount of the damping load tank causes the same effect can increase the internal resistance of the tank. The effect of the damping can be overcome by amplifying the regenerative feedback. Figure 2.3 shows the effects of damping, undampened oscillation, and 2.3b shows the effects of damping, oscillation, and tuned circuits having lower series resistance, and oscillations in tuned circuits having high series resistance. Figure 2.4 shows a block diagram of the LC oscillator. Note the oscillator contains the three basic requirements: sustained oscillation, amplification, frequency determination device, and regenerative feedback. Alright, feedback goes from in and output and frequency determining device and amplifier. The amplifier supply of the energy to the beginning, known for the flywheel effect. With the flywheel effect, with the maintenance oscillation in the circuit is intervals between the pole and excitation energy. Recall the chapter 1 of the tank circuit is alternately stored within the inductor capacitor. The inductor capacitor network provides an initial oscillation portion from the output of the LC network that is then returned to the input of the amplifier regenerative feedback network to sustain the oscillation. When the tank circuit is used to develop oscillation as an oscillator, the output frequency of the oscillator primarily with the resonant frequency tank circuit that can be found in the formula frequency. Resonant frequency is equal to 1 over 2 pi square root of the induction capacitation times. And the crystal, another frequency determined device with the crystal may be used with a tank with a circuit that may be performed alone. Crystal exhibits the crystal known as the piezoelectric effect. The piezoelectric effect is a property of the crystal which the mechanical force produce electrical charge, but conversely with the electrical charge produced with the mechanical force. The effect is formed the oscillation similar to the flywheel effect with the tank circuit. The piezoelectric effect can be seen in a number of the crystal substances. The most important of these mineral quartz of the Rochelle salt. The quartz does not exhibit the piezoelectric effect over the degree of the Rochelle salt does. Quartz is used for the frequency control oscillators because of its greater mechanical strength. The mineral tourmaline is a physical strength longer, like physically strong like quartz, but because it's more expensive, it is not used in the field determining device. The discussion will be to deal with the quartz crystal. Crystals using an oscillator circuit with a thin sheet wafer from the normal synthetic quartz for the ground with a specific thickness to obtain the desired resonant frequency. Crystals are mounted in the holder support with the physical even provided with the electrodes, but the voltage is applied, but the holder must allow the crystal freedom of vibration. Therefore, many different types of holder. One type is shown in Figure 2.5. 2.5 shows the crystal holder. Also, the frequency of the crystal ground referred to as the natural resonant frequency of the crystal. Voltage applied with the crystal produces the mechanical vibrations, which in the turn produce the output voltage naturally resonant frequency of the crystal. A vibrating crystal can be represented with the equivalent electrical circuit component of the capacitation inductance resistance. Figure 2.6 view A illustrates the symbol of the crystal shown in view B shown the equivalent circuit for the crystal. View C showed the equivalent circuit for the crystal and the holder. C capacitor 1 represents the capacitance between the metal plate of the holder. So for the crystal and electrodes with the symbol, with the crystal electrode symbol, crystal symbol equivalent circuit with the equivalent circuit and inductor capacitor resistor 1 capacitor 2, capacitor 1, inductor for resistor 1 holder added. The merit The merit of the crystal is many times greater within the LC strength circle. The higher the merit is, because of the resistance of the crystal extremely small. With the commercially produced the crystal with the range of the merit within 5,000 30,000. The high merit and cover the frequency stability is much greater than the ordinary LC tank circuit for the region. With the crystal is used with the mainstay sim wave generated circuits. Are your solid-state oscillators. As you've just studied, the basic oscillator can be broken down in three main sections: the frequency determinant device, the amplifier, feedback circuit. The frequency determinant device for the LC oscillators, usually the LC tank circuit. Although the tank circuit is normally defined input circuit for the oscillator, both electron tube and transistor sometimes appear with the output circuit. The difference for the magnitude of the plate with the collector currents and shutting the impedance for the consideration in the design location for the such tank circuit in both solid-state and electron tube circuit. The oscillator takes the place in the tune circuit. Both electron tubes and the transistor function primarily with the electrical value of the amplifier automatically delivered the input circuit. The proper amount of the energy to sustain the oscillation in both tubes, the transistor oscillator feedback circuit coupled with the energy of the proper amount with the correct phase of the output and input circuit is the same oscillation. Feedback. Let's review what you have studied up to this point with concerning the feedback process of the transferring energy with a high level of the point with the system and a low level of the point system. The means of the transferring enemy output of the amplifier back into its input. If the output feedback signal output with the input signal is degenerated negative feedback. However, the feedback in the aids the input signal of the feedback is called regenerative positive feedback. Regenerative is a positive feedback, and one with requirements such as oscillations in the oscillator. The feedback can be applied in several ways to reduce practical oscillator circuit. Types of feedback. Chapter 1 discover the resonant and the tank circuit how the sinusoidal signal is generated by the action of the inductor capacitor. The feedback signal is coupled with the circuit to be either of the two means. First method takes some of the energy from the inductor that can be done by any one of the three ways we shown in Figure 2.7, the view A, view B, and C. And the oscillator U with the particular coil with the shown view A with the referred to the Armstrong oscillator. When the oscillator U with the tap coil with the view B and the split coil with view C, the referred to as the Harlot oscillator. The second method of coupling the feedback signal is U with the two capacitors with the tank circuit with the tap with the feedback signal between them. This is shown in view D. The oscillator U with the method is referred to as the Colpitts oscillator. Each of the particular oscillators is named after the person who had originally designed them. Our Figure 2.7 shows the feedback signal with the tickler coil with the feedback signal, the tap coil with the feedback signal, the split coil feedback signal with the split signal. Configuration of the oscillator. Any of the three basic amplifier configuration, common collector, common base, common emitter that described in Neets Module 7 Introduction Solid-State Device Power Supply Chapter 2 may be used with the oscillator circuit. However, they can be, certain consideration amplifier of the circuit such as the operation frequency and the output of the power required usually determine which of the three configurations to be used. The three basic configurations shown Figure 2.8, View A, B, and C. Once again, that was tickler coil, tap coil, split coil, and split capacitors. Alright, Figure 2A shows the basic configuration, common collector configuration, feedback network, 0 degrees phase shift to the amplifier. Then to the amplifier has a frequency determinant device, and the amplifier also goes to the power supply. Alright, your basic configuration, base configuration, feedback network, shift 0 to the amplifier, and then the frequency determining device of the power supply. Common emitter configuration, 180 degrees feedback and phase shift to the amplifier, then the frequency determining device and power supply. Common collector configuration. Since there is no physical phase reversal between the input and output circuit of the common collector configuration, the feedback network does not need to provide a phase shift. However, since the voltage gain is less than unity, power given is low. Common collector configuration is very seldom used with the oscillator circuit. The common base configuration, the power and voltage gain with the common base configuration with a high enough to give the satisfactory operation oscillator circuit. The wide range between the input resistance and the output of the resistance make the impedance match that is slightly harder to achieve in the common base circuit than in the common emitter circuit. An advantage of the common base configuration exhibits for the base a high frequency response that does the common emitter configuration. Common emitter configuration. The common emitter configuration has high power gain used with low frequency applications have the energy with it, which is feedback with the output, and then to be favored the energy is the input feedback network. Common emitter oscillator must provide a phase shift of approximately 180 degrees. An advantage of the common emitter configuration is that medium resistance range of the input and the output simplifies the job of the impedance matching. Oscillator circuits. Oscillators may be classified by names such as the Harley Colpus and manner with which the DC power is applied to oscillators, in which the DC power is supplied with the transistor through the tank circuit. The portion of the tank circuit is said to be a series fed. Oscillations receive the DC power with the transistor through a path that's separate with the parallel. The tank circuit is said to be parallel field shunted or parallel or shunted field. All the oscillators in the chapter can be constructed in either way by series or shunt fed, but the construction depends on the character for the oscillator circuit and the designer interested in. Series fed and tuned collectors. Armstrong oscillators are illustrated in Figure 2.9 View A. The DC path from the negative side of the ground is the voltage of the capacitor collector, or the voltage of the common collector for the resistor of the emitter. The transistor 1 and transformer 1 back to the positive side of the voltage of the common collector. The figure clearly illustrates both the AC and DC components through the tank circuit. Our figure 2.9a shows the series shunt fed tuned collector Armstrong series fed. Transistor 1 negative positive transistor common emitter. The base is read to the induction coil. The induction coil goes down to the capacitor. Resistor and resistor E, capacitor E, and go to the emitter or the base, Or the monotonic circuit slightly is become with the shunt fed with the tune collector for the Armstrong oscillator shown with the view B with the DC components filed with the ground with the resistor voltage over the transistor 1 power with the voltage common collector with the DC is blocked with the tank circuit with the capacitor 2 with only an AC component flowed with the tank circuit. Figure 2.9b shows the series shunted front tune collector Armstrong oscillator shunt fed. The function of the oscillator is to produce the sinusoidal wave shape with a specific frequency and amplify. Doing so, the stability of the oscillator is very important. Depending on its application, oscillator may be required to have either good frequency stability with amplitude stability. In many circumstances, both are required. Only over the two good frequency stability, you would consider more important. Frequency stability of the oscillator is measured with the degree with which the constant frequency output is approved. The better the frequency stability, the closer the output will be to the constant frequency. The frequency instability variations above and below the desired output frequencies may be covered with the transistor character of the variation external circuit elements. The stated before, output power is not prime importance. Transistor oscillators may be based on bias class A to ensure the stability with minimizing distortion. When this is done, the DC operating point established by the power supply is shown so that the operation for the transistor oscillator curve over the most linear portion of the transistor characteristic curve. The operation of the circuit falls into a nonlinear portion of the characteristic curve of the transistor. Parameters, voltages, and currents vary. These parameters are basic stability, frequency of the transistor oscillator. Operating frequency variations may occur with the change of these bias voltages. Thus, the constant supply of the voltage and primary requirement of the good frequency stability, even the common base source of the both collector and emitter electrodes, result in the relatively constant radio of the two voltages. In effect, the changing one voltage then somewhat counteracted by the change in the other. The counteraction takes place because of the increase of the collector voltage causes the increase of the oscillation frequency, increase of the emitter voltage causes the decrease in the oscillating frequency. This results in changing capacitance between the junction of the transistor. However, the common base bias source does not completely compensate since of the effect of the other circuit parameters of each of the bias voltages differ. Just as in any transistor circuit with a change of the transistor operating point with a change of the temperature with an encounter with the transistor oscillator, the effect of the change of the temperature are called the collector for the current to increase the transistor and not stabilize. The increase of the collector current that can be prevented by the reducing forward bias with the amplitude stability. Amplitude stability of the transistor oscillator indicates the amount with which the actual output without amplitude varies with the desired output amplitude. The same parameters voltage current with the effect of the frequency stability, they also affect the amplitude stability. Output amplitude may be kept relatively constant by ensuring the feedback is large enough for the collector current is maintained proper level of feedback. Even the main manner makes the output of the voltage directly proportional to the supply voltage. These regulations of supply voltage ensure the good stability, amplitude stability. Or your Armstrong oscillator. The Armstrong oscillator is used to produce in-wave output with a constant amplitude with a very fairly constant frequency with the radio frequency changes. If you generally use the local oscillator with the receiver that is the source of signal generated with the radio frequency oscillators maintain medium, high, and frequency range. The identifier character for the Armstrong oscillator is that one is using the LC tune circuit to establish frequency oscillation feedback with the accomplished mutual inductive coupling between the tickler coil and the LC tune circuit. 3 is using this Class C amplifier with a self-base if the frequency of the very stable output amplitude is relatively constant. Views A, B, and C shown in the figure 210 can be used to build the basic Armstrong oscillator. View A shows the conventional amplifier. The resistor 2 provide the force bias for the transistor 1. The capacitor 2 is coupling the capacitor to the inductor 1 and the resistor 1 and for the collector load impedance for the common emitter for the configuration with it provides a 180-degree phase between the base and collector. So in your you have your voltage current collected with the resistor 2, with the capacitor 2, with the going into the base, the emitter grounded, and the collector on the resistor and the resistor 1 and an adjustable rheostat and induction coil on the voltage current collector positive, both base and current collector emitter grounded. Frequency determination of the range is the capacitor, the capacitor inductive of the basic Armstrong feedback network. Inductive coil 1, inductive coil 2, rheostat resistor, and a special capacitor, quartz capacitor, I think that is. UB showed the frequency determined component of the inductor L with the 2 with the capacitor 1 the variable tuning, which would give you the resonant frequency desired value. You see, so this one right here is a tune capacitor, is a tune circuit, a tune capacitor. If you see with the feedback network, the U of the L1 the collector lobe with the primary, the L2 is the inductive coil 2 is a secondary one coupling the transformer to provide a 180-degree phase. Variable resistor 1 control the amount of the current through the inductive current 1. The resistor 1 adjusts the maximum resistance method of the current flow of the induction 1. The transformer now coupled the maximum signal to represent the large feedback amplitude tank circuit of the inductive 2 in capacitor 1. The resistor 1 adjusts the small resistance less current flow for the inductor 1. Less energy is coupled to the tank circuit. Therefore, the feedback of the amplitude decrease for the resistor 1 normally adjusted so the inductor 1 current is adequately sustained tank oscillation. View D show the complete oscillator circuit with connecting the feedback network through the coupling of the capacitor to the base of the transistor 1 forms the closed loop of the feedback shown within solid arrows. Lets the very rare with the feedback regenerate with the assume the positive signal of the base of the transistor 1. The transistor conduct heavy with the forward bias of the current flow with the inductive of the resistor coupled with the voltage coupled with the inductive 1 to increase the voltage increase it with the inductive of the coupled with the inductive 2 and inverted action ensure the voltage pop with the base end with the inductive 2 and induction winding 2 with the capacitor 1 with the phase of the base voltage of the positive volt signing of the signal is now coupled with the capacitor 2 with the base of the transistor 1. The regenerated feedback of the office for the damping of the frequency determine the network with a sample sufficient amplitude to provide circuit again. Circuit and view deed all the 3 requirements for the oscillator amplitude frequency determining device regenerated feedback the oscillator schematic drawing and the tune of the base oscillator because of the frequency determining device is in the base circuit. The frequency determining device for the collector circuit will be at the tune collector oscillator. The circuit is viewed with the D between the Armstrong oscillator. Figure 210 show the view D. The following discussion circuit operation Armstrong oscillator. The voltage current collector is applied with the circuit the small amount of the base current flows for the resistor 2, which sets the forward bias of the transistor 1. The forward bias collector current is to flow through the ground through the transistor 1, resistor 1, and inductive current 1 to the voltage collector. The current through the inductor 1 develops a magnetic field, inducing the voltage of the tank circuit with the voltage positive at the top of the inductive 2 and induction winding 2, capacitor 1. At this time, the 2 actions occur. First, the resonant tank circuit with the capacitor 1 chart of the change the chart of the voltage of the tank circuit is now stored energy. This sending the coupling of the capacitor 2 with the coupled positively signal with the base of the transistor 1. A positive signal on the base of the transistor 1 conducts harder. The conductor 1 conducting harder more frequently than flow through the inductor 1. Inductive winding 1 large voltage then induced the inductive winding number 2. The large positive signal of the coupled feedback base then back to the base of the transistor 1. While this is taking place, the frequency determining device is storing more energy with the capacitor 1 is charging the voltage and introducing the inductive current 2. The transistor will continue to increase the conduction until the reach of the saturation. As saturation, the collector of the current transistor with the maximum value cannot increase it any further. The steady current of the inductive 1 magnetic fields are not moved with no voltage induced in the secondary. With no external voltage for the capacitor 1 act the voltage source of the discharge of the voltage across the capacitor 1 decrease the energy of the transformer of the magnetic field of the inductive 2. Now let's look at capacitor 2. The coupling capacitor of capacitor 2 is charged approximately the same voltage capacitor 1. Capacitor 1 discharge of the capacitor 2 discharges the primary discharge path of the capacitor 2 through the resistor 2 show over the dash arrow of the capacitor 2 discharge of the voltage drop of the resistor 2 both the force bias for the transistor 1 collector current begins to decrease the cause of the decreasing positive potential for the base of the transistor 1. The decrease of the collector current allows the magnetic field of the inductive 1 to collapse the collapsing field of the inductive 1 Coil 1, induct with negative voltage with the secondary 1 with a capacitor 2, the base of the transistor 1 more negative again with the regenerative action continue with the transistor 1 is driven into a cutoff. When the transistor 1 cut off, the tank circuit continue with the flywheel oscillation. The flywheel effect not only produces the same wave signal, but keeping the transistor 1 cut off with the feedback with the oscillation inductive 2 and capacitor 1 would be dampening out after the several cycles. To ensure the amplitude of the signal remains constant, the regenerative feedback is supplied with the tank. Each one of the cycle has 5 of the voltage of capacitor 1 reach the maximum volt negative, and the capacitor 1 give it the discharge of the towards 0 volts. Transistor 1 still become below the cutoff of the capacitor 1 the discharge of the 0 volts becomes positively charged. The tank circuit with the voltage again the coupled to the base of the transistor through the base voltage becomes positive. Allows the collector current through the flow of the collector current creates a magnetic field in the inductive capacitor 1 coupled in the tank. The feedback action replaces any lost energy in the tank circuit drives transistor 1 towards the saturation. After the saturation is reached, the transistor is again driven into the cutoff. The operation of the Armstrong oscillator is basically this. The power applied with the transistor allows the energy to be applied with the tank circuit to cause it to oscillate. Only every cycle transistor conducts a short period of time. Classic C operation returns enough of the tank to ensure constant amplitude output signals. Class C operation, high efficiency low loading character. The longer the transistor 1 is cut off, the less loading of the frequency determining device. Figure 211 shows a tuned-based Armstrong oscillator will probably see with a resistor 3 will the add to improve the temperature of stability. Bypass the capacitor 3 prevents degeneration. Capacitor 4 output coupling capacitor is an impedance matching transformer 2 provided the method of the coupling output signal. The transformer 2 is usually loose coupled radio frequency transformer which reduces undesired or reflected impedance of the load back to the oscillator. Alright, so you have adjustable rheostat 1, inductive coil 1, transformer 1, tapped, L2, inductive current grounded, capacitor 1, tuned capacitor 1 on the transformer, and the rheostat, also on the voltage current collector on the base of the transistor. The emitter is going to a resistor and collector and resistor 3 and collector 3, which keeps the resonant frequency, and capacitor 1, capacitor 4, and the resistant 2, the inductive coil 3 and 4 also create a bigger your amplification. The Armstrong oscillator is shown how the Class C amplifier can produce the sim wave output but is not distorted. Another class operation nonlinear many harmonic frequency generated. The only frequency received enough of the gain of the cover the circuit to oscillate the frequency of the resonant tank circuit. Thus, the high frequency undistorted output signal is determined. The waveforms in Figure 212 illustrate the relationship between the collector voltage with the collector current. Note that the collector current flow for only a short time during each cycle. When the tank circuit is oscillating, Figure 211, the inductive capacitor over the primary transformer and the inductive capacitor 1 acts as a secondary signal tank. Therefore, the coupled transformer of the coupling capacitor C4 output with the voltage across the inductive 4 and sim wave. Alright, you figure 2/12 of the collector current voltage of the cross of the Class C oscillator voltage current collector, amperage current collector. Notice it's on the bottom out face. Your Hartley oscillator is an improvement of the Armstrong oscillator, although the frequency stability is not best possible with all the oscillators. Hartley oscillator can give the can generate a wider range of frequency, very easy tune. The Hartley will operate with the Class C with a self-bias ordinary operation. Class A with the output waveform must be constant voltage level of the linear wave shape. The two versions of the oscillator with the series fed and shunt feedback. Series fed and shunt fed. The main difference with the Armstrong and the Hartley oscillators lies in the design of the feedback. Particular coil with the separate the coil with the knot in issue. Instead of the Hartley oscillator with the coil with the tank circuit is split with the inductor current flow with the one section of voltage and the other section of the developed feedback. Alright, your series Hartley oscillator. One version of the series fed Hartley oscillator shown in Figure 213. The tank circuit consists of the two tap coil, inductive 1 and inductive 2. Capacitor 2 with the feedback circuit is shown with the tank circuit with the base of the transistor 1 through the coupling capacitor of the capacitor 1. Coupling capacitor 1 prevents low DC resistance and inductive winding L2 with the placing short across the emitter base junction. Resistor voltage of the capacitor of the capacitor 3 bypass in wave signal around the battery. Resistor voltage used with the temperature stabilization to prevent thermal runaway. Degeneration is prevented with the capacitor voltage in parallel with the resistor voltage. The amount of the bias is determined the value of the resistor bias. The emitter base collection, small amount of the DC resistance of the inductive coil 1 and the resistor voltage. Our figure 212 shows the series tuned shunt capacitor, shows the tuning capacitor 2, the inductive resistor capacitor with the resonance frequency in between the inductive coil 1 and 2 capacitor and resistor bias, holding the transformer, keep making the transformer Q1 non-positive negative pass frequency with the capacitor 3 and inductive coil and the voltage current collector. When the voltage is applied with the circuit with the current of the battery flow with the coil 1, inductive with the emitter with the resistor voltage with the current flow with the emitter with the collector back to the battery, the surge of the current flow of the coil 1, inductive with the voltage with the inductive 2, the start of the oscillator within the tank circuit. When the circuit is first started through the flow of the inductive 1, the bottom of the inductive 1, negative with respect to the top of the inductive 2, the voltage using the coil 1 and coil and inductive 1 2 makes the top of the inductive 2 positive. The top of the inductive 2 becomes positive. The positive potential is coupled the base with the transistor 1, capacitor 1. The positive potential of the base result with the increase the forward bias of the transistor 1, cause the collector with the current to increase the collector current. Increase the emitter current flowing through the inductive coil 1, and if they increase the current through the inductive coil 1 result of the energy being supplied to the tank circuit, which in turn increase the positive potential of the top of the tank of the inductive 2, increase the forward bias of the transistor 1, they actually continue with the rate of the current chain of the tank with the increase the forward bias of the transistor 1, they actually continues until the rate of current chain through the coil inductive coil 1 no longer increase the current through the coil 1 inductive transistor cannot continue the increasing indefinitely with the coil and transistor will burn up. Circuit must be designed with a proper selection transistor associated with the sum point with the reach of the current through the no longer continue increase the point of the circuit capacitor 2, the chart with the potential across inductive 2 and inductive 1. 1 and 2. This is shown that heavily guided with the base wave form. The current for the inductive 1 increase the voltage of the inductive 2. The positive potential current of the tank begins with the decrease of the capacitor 2 and starts the discharging inductive coil 1 and 2. This action maintains current flow with the tap coil caused the decrease of the forward bias of the transistor 1 in turn with the decrease of the forward bias of transistor 1. Causes the collector and emitter to current with the degree of the instant of the potential current of the tank circuit. The degree of the zero, the energy of the tank circuit is then contained in the magnetic field of the coil. The oscillator has been completed a half cycle operation. Next to the magnetic field of the inductive capacitive inductive winding to collapse of the current of the capacitor to the top of the action from the collapse of the magnetic field of the cause of the top of the inductive 2 to become negative. The instant negative charge of the capacitor 2 to begin with the charge of the opposite direction. Negative potential is coupled with the base of the transistor 1 output with the forward bias of the transistor oscillation operated with the class A. Therefore, the positive negative signals applied with the base of the transistor 1 will not cover to go into saturation cutoff. Will the tank circuit the reach of the maximum negative value of the collector and emitter currents will still be represented with the minimum value. The maximum magnetic field will have collapsed. The oscillator will have completed 3/4 of the cycle. At this point, the capacitor 2 begins with the discharge, decrease the negative potential at the top of the inductive winding 2. The point potential will be in the positive direction. Negative potential applied to the base of the transistor 1. Decrease the opposition forward bias. Also, the decrease the fact cause of the forward bias to begin with the increase of the result of the increase the emitter with the current collecting with the inductor 1. The increase of the current with the inductor 2 1. Cause the additional energy to feedback with the tank circuit. Replace with the lost energy. Energy lost in the tank replaced with the equal large amount of the number of energy. Oscillation will be sustained. Oscillators have known to be complete and has not completed one cycle and will continue to repeat over and over again. Alright, your shunted Hartley oscillator. Version of the shunt-fed Hartley oscillator, shunt figure 214. The parts of the circuit become the basic function for the the counterpart for the series of the Hartley oscillator. The difference between the series-fed shunt-fed circuit is that it does not know how to flow through the tank with the circuit. The shunt-fed circuit operation is essential with the same series of the feed-fed Hartley oscillator as when the voltage is applied with the circuit. The transistor 1 starts conducting collector current with the transistor 1 increases the change and increase the couple of the capacitor 3. The tank circuit causes it to oscillate with the capacitor 3 is also adds an isolation capacitor to prevent the DC from flowing through the feedback coil with the oscillation as the collector will be compacted with the capacity feedback to energy lost within the tank. Figure 214 shows the shunt field tune based Hartley oscillator. Shows capacitor, the tuning capacitor, inductive 1 and 2, in single voltage collecting current, capacitor voltage, resistor voltage, and that makes your frequency resonancy going into the voltage. The transistor 1, the emitter going to the voltage, common emitter without voltage frequency resonancy. Your base going to resistor base, and then the common emitter with the inductive coil running on the field, same shunt field, the same circuit as the the voltage and the inductive capacitor 3, and your Colpitts oscillator. Both Armstrong's Hartley oscillators have the tendency to be unstable. The frequency between the junction capacity of the comparison with the Colpitts oscillator has a fairly good frequency stability, easy to tune with can be with a wide range frequency, large value with the capacitance, with a parallel of the junction, minimize the effect of the frequency stability. Colpitts oscillator is very similar to the shunt-fed Hartley oscillator, except that the two capacitors are used the tank circuit instead of the tap coil. The Hartley oscillators has a tap between the two coils. The Colpitts has the two taps has a tap between the two capacitors. The change of the frequency of the Colpitts either vary the inductance of the coil, vary capacity of the two capacitors in the tank circuit. Notice that no coupling with the capacitors between the tank circuit of the base of the transistor 1 and capacitor 1 and 2. The tank circuit are in parallel with the input and output inter-element capacitance between the emitter and base collector of the transistor with the input and the output collective capacitive effect of the minimum of the tank circuit. Better frequency stability can be obtained with the Armstrong-Hartley oscillator. Alright, for 215 show your Colpitts oscillator, you have your resistor voltage capacitor voltage with the response frequency of the emitter. What was it called? I don't know what it's called. The amperage voltage would be in the inductive coil 1 and the capacitor 1, 2. And then your outside capacitor voltage resistor bias on the transistor 1, which figure 216 shows the common base Colpitts for the oscillator. You the positive, negative transistor amplifying device. Note with the virtue of the Colpitts oscillator regenerate feedback of the tank with the tank circuit and apply with the emitter with the base bias for the provide with the resistor of the resistor bias, resistor frequency, resistor capacitor. Capacitancy is collector load with the resistor of the voltage developed with the input signal axis of the emitter swapping resistor 2 with the circle with the consider the capacitor 1, capacitor 2, in parallel with the primary winding transformer 1 winding. The voltage of the developed with the capacitor 2 with the feedback with either both of the capacitor of the bolt may be adjusted with the control of the frequency of the common base configuration. There's no physical difference between the signal at the collector and the emitter signal, therefore the phase of the feedback of the signal does not have to be changed with the emitter. Swing the negative of the collector, also swing the negative of the capacitor 2, charge the negatively of the junction capacitor 1 and capacitor 2, the negative charge across capacitor 2, feedback to the emitter, the increase of the feedback reversed by the transistor 1, the collector of the reverse transistor 1 becomes the more negative of the capacitor 2, because it becomes negative potential feedback effect with the continuity until the capacitor of the collector of the transistor 1 is unable to become any more negative. At that time, the primary transformer 1 winding will act source to cover the normal tank circuit. At the field collapse, the tank potential reverses, and capacitor 1 and capacitor 2 will begin to discharge. The capacitor 2 becomes less negative. The reverse bias of the transistor 1 increases the collector voltage swings in the positive direction. Capacitor 1 and capacitor 2 will continue to discharge the charge of the positive direction. The positive going voltage across the capacitor 2 will give the feedback with the emitter to regenerate feedback. This will continue until the field around the primary with the transistor 1 collapses. At that time, the collector with the transistor 1 will maximize the transformer 1 collapse. At the time, the collector with the transistor 1 will maximum positive value, and the capacitor 1 and capacitor 2 will begin to discharge potential for the junction will become less powerful. The increase the reverse by the transistor 1 drive the collector negative with the causing capacitor 1 and capacitor charge the negative direction, and repeat the cycle. Alright, 216 is your common base Colpitts oscillator. Resistive capacitive feedback oscillator. As mentioned earlier, the resistive capacitor networks provide with negative feedback will determine the frequency operation. Resistive capacitive oscillator. The oscillator presented with this shaft have in the resonant tank circuit with its inductive capacitive. They should always also know that the inductive capacitive tank circuit stores energy alternately in the inductor capacitor. The major difference of the inductor capacitor and the resistor capacitor is the frequency determinant device of the resistor capacitor is not a tank circuit. Remember, the inductive capacitor can operate with a class A or class C bias. Because of the oscillator acting on the resonant tank, the resistor capacitor, however, must use the class A bias because resistor capacitor frequency determinant device does not have oscillating ability of a tank circuit. Alright, resistor capacitor feedback of the phase shift of the oscillator shown in figure 217. Components of the capacitor 1, resistor 1, capacitor 2, resistor 2, capacitor 3, and resistor bias are the feedback frequency determination network. The resistor capacitor network also provides the need for the phase shift between the collector and the base. Alright, so capacitor 1 is a 60 degree phase. Capacitor 2 and resistor 2 is 180 degrees phase. Capacitor 3 and resistor bias on the resistor frequency, resistor voltage with the capacitor on the base and the emitter of the positive negative transistor makes up the 360 degrees, and the transistor one, that signal that was fed through the capacitor feedback, the feedback from the transistor of the base and the collector goes to the common current collector out. Resistor current and resistor frequency and resistor voltage and capacitor acts as a tune sinker voltage current collector grounded. Alright, your phase shift oscillator. The phase shift oscillator is shown in figure 2.7 the same wave generated with the resistor with capacitor network and frequency determined device. We discussed earlier with the common emitter amplifier configuration. This is the 180 degrees phase difference between the base and the collector signal. To obtain the regenerated phase of the shift oscillator, you need a phase of 180 degrees between the output and the input signal. The resistor capacitor network consisting of the three resistor capacitor sections provided the proper feedback of the phase inversion and provided negative regenerated feedback. Each section shifted the feedback signal 60 degrees in phase. Since this impedance the resistor capacitor path of current flowing through the leads applied with the voltage specific phase angle. Phase angle is determined the amount of the resistant capacity of the resistor capacitor section. If the capacitation is fixed value with the chart of the resistant value will change with the phase angle, and if the resistance could be changed with 0, then we could get a maximum phase angle that's 90 degrees. But since the voltage cannot be developed across the resistance of negative 90 degree phase shift is not possible. With a small value with the resistance, however, the phase angle of the phase shift is less than 90 degrees for the phase shift of the oscillator. Therefore, the three resistor capacitor sections are needed to give the required 180 degree phase shift of the regenerated feedback. The value of the resistant capacity are generally chosen by each of the phase section provided with the 60 degree phase shift. Resistor bias, the resistor forward and resistor capacitor provided the bias for the collector bias. Capacitor voltage bypass the variation around the emitter of the capacitor emitter with the bypass of the variation of the emitter of the resistor emitter. Capacitor 1, 2, and 3, resistor 1, resistor 2, and resistor bias form a feedback with a phasing shifting network. Resistor 2 variable with a fine tuning compensate with a small change at the end of the value with the other components phase shift network. Or when the power is applied with a circle of the oscillation are started by any random noise, random electrical variation, generally internally electronic component of the chain with the flow of the base of the current result with the amplified chain with the current collector with a phase shift with 180 degrees. The signal is returned to the bias between shifted 180 degrees between the action of the resistor capacitor net with the making the circle of the regenerated view A figure 218 show the amount of phase shift produced in capacitor 1 resistor 1 view B show the amount of phase shifted and produced in capacitor 2 capacitor 3. Capacitor 2, resistor 2, or shift the signal received with the capacitor 1, resistor 2. View C show the complete phase of the signal leave the resistor capacitor network. With the current amount of resistor capacity with the phase shifting network, the 180 degree phase shifting only with the one with the frequency, any other desired frequency capacity, reactancy, decreasing causes the incorrect phase. The relationship of the feedback between the becomes degenerated. Thus, the oscillator works only in only one frequency. To find the resonant frequency of the resistor capacitor phase shift the oscillation, use the following formula. Resonant frequency is equal to 1 over 2 times pi times the resistor times the capacitor times the 2 times the number of resistors. I believe that's what the N would stand for. Our 218 show the 3-section phase shifting resistor capacitor phase shifting capacitor 1 and 2 60 degree angle the phase shift the capacitor 2 and 3. And then you have your 3-section, which was actually 3 different resistors on a RC network phase shift network causing 180 degrees phase. High generated transit may speed with a 3-section resistor capacitor because of the loss of the network are high. Use more lead with the resistor 3-section resistor capacitor section reduce the overall single loss within the network. This because of the additional resistor capacitor section reduce the phase shift necessary to each for the section. Those loss of each section is lower the phase shift that reduces additional with the oscillator with the U of the 4 more resistor capacitor networks more stability than the ones with the 3 resistor capacitor networks and 4-part in their resistor capacitor networks. Each phase is shift phase feedback. The signal is approximately 40 degrees, 5 degrees to give it the total required of 180 degrees phase shift. Alright, crystal oscillators. Crystal oscillators are those with a specially cut crystal control of the frequency. Crystal controlled oscillators are standard means for the maintaining frequency of the radio transmitting stations with the assigned frequency limits. Crystal controlled oscillators produce the output with a high stability, very precise frequency. As stated earlier, crystals are electrical circuits with a thin sheath that cut through. The natural crystals are grounded to proper thickness of the desired resonant frequency for any given crystal cut. The thinner of the crystal, higher frequency resonant frequency. The cut, X, Y, A, T, and so forth. The crystal means that the price the way which the usable is cut. The necessary crystal with some typical crystal cuts may be shown in Figure 219. Or you have your XY and X and Y cut, which is horizontal, vertically, or AT cut. Transmitter will require a very high degree of the frequency stability with the broadcast transmit with the temperature control over the maintained with the constant crystal temperature. The ovens are thermostatically controlled with the containers with the crystals are placed typically on the type of the cut to determine the active of the crystal. The crystal vibrates more than once the frequency, thus will operate the harmonic frequency. Crystals which are not uniform thickness may have two or more resonant frequencies. Usually one resonant frequency is produced, but not more pronounced than the others. The other less pronounced resonant frequency is referred to as a spruce frequency, sometimes with the crystal oscillating with two frequencies at the same time. The amount of the current safely passed through the crystal ranges from 50 to 200 milliamperes. When the rate of the current is exceeded, the amplitude of the mechanical vibration becomes due to the great, and then crystal may crack. Overloading crystal effect of the frequency vibration becomes the power of the dissipation. Crystal temperature increase the amount of load of the current. Crystals is a tuned circuit. As a crystal structure, the equivalent circuit shown in Figure 220 view A, B, and capacitor 2, and the inductor 1, resistor 1, view B represent the equivalent of the crystal quartz crystal in view with the A, with the capacity C1 view B represent the capacity between the capacitor electrodes view A. Depending upon the circuit character for the crystal, can active with the capacitor and inductor share with the tune with the circuit of the parallel tuned circuits. Alright, so you have your capacitor crystal electrodes. And the quartz crystal equivalent circle is capacitor 1, capacitor 2, inductor coil, resistor 1. In some frequency, reactive, the equivalent capacitor of the inductor of the end will be equal with the capacitor will act as a series tune circle. The series tune will have the minimum impedance of the resonance Figure 221. Above the resonance series tune circle acts inductively because the resonance acts capacitively. In other words, the crystal until it has low impedance with the series resonance frequency, the impedance increases with the frequency lowered because of the action of the capacitor. The impedance for the crystal until the increase of the frequency is raised. The series resonant point and because of this until it is an inductor. Therefore, the crystal unit it reacts as a series tuned circuit. Figure 221 shows the frequency response of the crystal, the impedance of the series, the resonancy, the capacity of the inductive, passive, and parallel resonance frequency. Since the series of the tuned circle acts with the inductor above the resonant point of the crystal unit becomes the equivalent of the inductor parallel, the equivalent of the capacitor 1 view B, the Figure 220, at the same frequency above the series resonant point of the crystal until the acts of the parallel tuned circuit. Parallel tuned circuit has a maximum impedance of the parallel resonant frequency acts inductively below the unparalleled inductive unparallel resonancy. Therefore, the frequency of the depend upon the cut of the crystal and the crystal until the capacitor parallel tuned circuit. The frequency stability of the controlled oscillator depends on the merit of the crystal. The merit of the crystal is very high, it's more than 100 times greater than obtained with equivalent electrical. The merit of the crystal is determined with the cut of the type of the holder. Accuracy of the grinding commercial produced of the crystal range of the merit of 5,000, 30,000 with some laboratory experiments. The crystal range of merit was up to 400,000. Your crystal-controlled Armstrong oscillator. The crystal-controlled Armstrong oscillator uses the series tune mode of the operation that works with the much same as the hard-lit oscillators, except for the frequency stability is improved with the crystal and the feedback path. The operator oscillator is different in frequency, but you simply chain with the crystal, but each of the crystal operates different frequency. Our Figure 221, 222 show the crystal-controlled Armstrong oscillator. You have a crystal control, which would be Y1 on the base of the emitter, and the output between capacitor 2 and capacitor 1 is your tuning circuit of the capacitor 1 transformer, winding, tickler coil, voltage current collector, resistor bias, resistor voltage capacitor. That's the resonant frequency, and amplifier would be capacitor 2 on the tuned circuit with the resistor frequency, so that you get a oscillator. Variable capacitor C1 makes the circuit turntable to select with the crystal frequency circle 1 capacitor 1 capable of the tuning of the wide band with the select of the crystal ranges frequencies. Regenerative feedback of the collector and base through the mutual inductive of becoming the transformer 1 and transformer 1 provide the necessary 180 degree feedback of the signal of the resistor bias with the resistor forward bias and the resistor current provided the resistor collector provide the base for the collector base volt the capacitor voltage bypass the AC variation around the emitter capacitor emitter the AC variations around the emitter resistor emitter. A frequency above the below the series resistant frequency selected crystal impediment of the crystal and reduce the amount of the feedback signal to determine the prevent oscillation frequency of the other series resonant frequencies. Your crystal controlled Pierce oscillator. The crystal controlled Pierce oscillator uses the crystal until the parallel resistance circuit of the Pierce oscillator modified with the Colpitt's oscillator that operates. Same with the except for the crystal until the replace with the parallel resonance circuits for the Colpitt's. Figure 2/23 show the common base configuration for the base oscillator. Feedback is supplied with the collector with the emitter through the capacitor 1, the resistor bias with the resistor collect common emitter, and the resistor forward bias with the proper bias with the conditioned circuit with the resistor emitter with the emitter. The capacitor 1 with the capacitor capacitor emitter from the voltage of the divider of the connected across the output. But since there is no phase without the output of the common base emitter circuit, the capacitor 1 feedbacks the portion output signal of the emitter without phase shift. The oscillator frequency is determined not only by the crystal but also by the parallel capacity. You call it by capacitor 1 and the capacitor emitter. The parallel capacity affected by the oscillator frequency with the lowering it. Any change of the capacity of the capacitor 1 and capacitor emitter change of the frequency of the oscillator. Alright, figure 223 show the emitter going into the base is the resistor bias, your resistor emitter going into the transistor 1 emitter, capacitor emitter frequency, resonant frequency. Your oscillator would be over here on the voltage, the cutout, the current out, capacitor 1. Resonant radio resistor frequency and the capacitor 2 resistor bias emitter voltage current collector. Our figure 220 shows the common emitter configuration of the Pierce oscillator. The resistor circuit provided with the proper bias stabilization condition for the crystal unit with the capacitor 1, capacitor 2 determine the output frequency of the oscillator. The signal developed over the junction of the crystalline capacitor, the crystalline Pierce oscillator and capacitor 1 with 180 degree phase of the signal of the junction of the Pierce oscillator and capacitor 2, therefore the signal of the Pierce oscillator and capacitor 1 junction coupled back of the base of the transistor 1 regenerative feedback signal to sustain the oscillation. Alright, your pulse oscillator. Syncytial oscillation, same way is one that will produce output pulses as predetermined frequency in an indefinite period of time that operates continuously. Many electric circuits equipped with the radio requirement of oscillators be determined with a specific period of time that is remained the alpha condition until they're required at a later time. These circuits are referred to as pulse oscillators or ringing oscillators. There is nothing more than sine wave oscillator than turn on and off at specific times. Figure 225 UA show the pulse oscillator with the resonant tank with the emitter circuit and provides for the input makes the transistor 1 conductive heavily with the current flow with the inductive 1. There's no oscillation can be in play with the negative going input signal referred to if the gate if the cuts off the transistor 1 and tank oscillator until the gate ends until the ringing stops, which comes first. Figure 225 show the pulse oscillator, show the capacitor resistor on the base and the collector. Your output signal of the pulse oscillator going through capacitor and inductive parent grounded. Figure 225 show the timings of the T, time 1, time 2, time 3, output signal, time 1, time 2, and 3. Waves of UB, the waveforms in view B show the relationship of the input gate with the output signal through the pulse of the oscillation. The chief how the circuit operates. Assume the mirror of the inductive capacitor tank circuit is high enough to prevent the damping the output, but the circuit is obtained in an input gate that goes negative time 0 to time 1 and time 2 and 3. Remainder of time 1 and 2 conduct heavily, therefore no output of the circuit. The input gate control the time of the output circuit, making the gate wire cover the output to present a ring or longer time. Alright, frequencies of a pulse oscillator. Frequency is a pulse oscillator determined both of the input gate signal of the resonant frequency of the tank circuit with a synthesical oscillator resonant with the 1 megahertz, the output with a million cycles per second. In this case, the pulse oscillator number of cycles per resonant of the output will determine the gate pulsing width. In megahertz oscillators are cut off 1/2 a second to 50% of the time, then the output is 500 cycles with a 1 megahertz rate. In other words, the frequency of the tank circuit is still 1 megahertz, but the oscillators only produce 500 cycles each second. The output frequency can be determined by controlling how long the tank circuit will oscillate. For the example, the with a negative input gate with a 500 microsieverts power, the in gate with a 990,500 microseconds of a total 1 second apply. The transistor will cut off the 500 microseconds of the tank circuit will oscillate 500 microseconds, producing an output signal. The transistor will then conduct 999,500 microseconds of the tank circuit will not oscillate during the time period of 500 microseconds of the tank circuit will allow the oscillate until allowing only 500 cycles of the megahertz tank frequency. Or you can easily check the frequency value for the following formula. The time equals 1 over the resonant frequency of the tank circuit. One cycle of the resonant frequency. 1 cycle of the megahertz frequency is equal to 1 microsecond. Then dividing the time of the 1 cycle into the gate length of the 500 microseconds, you will get the number of 500. There are several different varieties of the pulse oscillator with different applications. Schematic diagram shown in Figure 225U for the emitter load pulse oscillator. The tank circuit can be placed in collector circuit, in which case they refer to the common collector load pulse oscillator. The difference between the emitter load and the collector load oscillator output signal of the first alternating emitter with the load but the not pulse oscillators given in the first alteration of the collector load pulse oscillators positive negative pulse. Positive issue for the oscillator will reverse the first alternation, both of the emitter load and the collector load oscillator. You probably have noticed now that feedback has not been mentioned in the discussion. Remember the regenerative feedback requirements of sustained oscillation. In this case, the pulse oscillator oscillations only require a very short period of time. Should they understand, however, the width of the input gate, which cuts out with the transistor, increase the amplitude, some way begins to get decrease the amplitude near the end of the gate. The period becomes the lack of the feedback of the long period of oscillation requires period. Particular application of the pulse oscillator will regenerate feedback, and the principal operation remains the same, except for the feedback network sustains the oscillation period with the desired amount of time. And I'm going to pause it and see how long this chapter is actually. We're going to finish up the rest of the chapter here. From your studies of oscillators, you should know that the oscillator will oscillate with the resonant frequency of the tank circuit. Although the tank circuit of the resonant particular frequency, many other frequency of the resonant frequency with a particular oscillator, the other frequency is referred to as harmonic. Harmonic defines the sinusoidal wave having the frequency that is multiple fundamental frequency. In other words, sine wave with the twice of the fundamental frequency referred to as second harmonic. When you must remember the current circuit operating with the resonant frequency, the relatively large amplitude harmonic frequency, the amplitude relatively small. For example, the second harmonic frequency, fundamental frequency with 20% of the amplitude of the resonant frequency, the third harmonic perhaps 10% of the amplitude of fundamental frequency. One of the useful purposes of harmonic frequency multiplication can be for the circuit with multiple fundamental frequency for the higher frequency need of the frequency multiplier circle. The result of the fact with the frequency stability with the most oscillating with the frequency increase with the relatively good stability can be achieved with the lower frequency. Thus, stability of the oscillator to operate at low frequency. One or more stage of multiplication has raised within the signal to desired operating frequency. Our frequency multiplication. Frequency multipliers are special class C amplifier made based on 3 to 10 times the normal cutoff bias. They are used to generate the frequency with a multiple harmonic low frequency. Some circuits are called frequency multipliers, harmonic generators. Figure 226 illustrated the frequency multiplier known as the frequency doubler second harmonic generator, illustrating the input with 1 megahertz output, 2 megahertz are twice the input frequency. In other words, second harmonic 1 megahertz, 2 megahertz. The third harmonic, third frequency tripler will be 3 megahertz, 3 times the input signal. The fourth harmonic quadrupler will be 4 times megahertz or 4 times 1 megahertz input signal. The fourth harmonic regenerated frequency quadruple normally has high multiplications, particularly at the harmonic higher than the fourth. The output diminishing the very weak output signal. Figure 226 shows the frequency doubler, the capacitor resistor frequency going the input with the base and the emitter going by to the ground, and then your tuning capacitor in an inductive coil versus current collector operator frequency doubler is multiplied by 2. Okay. Frequency multipliers operate with the pulse of the collector current produced with the Class C amplifier. Although the current, collector current flows in the pulse for the alternating collector voltage sinusoidal base curve, the action of the tank circuit, the output tank of the circuit is tuned to the required harmonic. The tank of the circuit also filter accepting desired frequency, rejecting all others. Or figure 227 to illustrate the waveform in a typical doubler circuit. You can also see the pole of the collector circuit with the same frequency input circuit with the pulse collector current, or energize the tank circuit with the cause of the oscillate twice with the base signal frequency between the pole of the collector current and the tank circuit continue to oscillate. Therefore, the tank circuit receives the current pulse for every other cycle as its output. Input voltage cutoffs and bias and collector current, so collector signal. Or your buffer amplifier. Coupling with the resonant frequency of the oscillator, different coupling method, the effect of the oscillator frequency amplitude, buffer amplifier, decrease the load affecting the oscillator, reducing the interaction with the matching impedance between the load and the oscillator. Figure 228 shows the schematic diagram of the buffer amplifier circuit over the common collector amplifier. The common collector amplifier has an input impedance for the low output impedance for the output of the oscillator is connected with a high impedance for the common collector amplifier. If the buffer has little effect on the operation of the oscillator, the output of the common electric buffer is then connected with the external load. Therefore, the change of the output load cannot be reflect back to the oscillator circuit. Therefore, the buffer amplifier reduces the interaction between the load and oscillator. The figure of 229 illustrates the shunt-fed Hartley oscillator with a buffer amplifier. The one way of the coupling sensor of the oscillator signal the couple forward with load change with the not coupled back to the oscillator. Or your input goes through capacitor 1, resistor 2, which is a phase split of the voltage current. I guess that was your I can't remember what that is. Voltage current coming from the collector, and then the emitter goes to the resistor for the output. The load, you have your amplification. Figure 229 shows the shunt field Hartley with the buffer amplifier. Summary of Chapter 2.